Hello everybody. Today we will be talking about frequency domain and frequency domain analysis and synthesis. Up to this point we've learned time domain methods. The basic separation here is based on the fact that in the time domain we use polynomials, we use settling time overshoot, specifications that are related to the time domain. And in the frequency domain, we have a different approach. We view the system from a different angle. Since we are dealing with the Laplace domain, we have some Laplace domain representations of these systems, which are based on the variable s. So in the frequency domain, what we do is we plug in some complex value instead of s, which is frequency dependent, and this frequency variable is most of the time omega. When we plug in this complex value, as you can see here, we plug in s equals j omega, which converts this into another complex valued function where the variable is omega. So basically we have omega that can vary in an interval, let's say from 0 to infinity, and we examine the system as a complex number that's varying with omega. So all the definitions and methods are more based on the body plot, since body plot is one of the most used frequency plots. Now you can think of this separation as in the time domain we might use the root locus plot, which is a plot that shows us the p-type controller based on the movements of the roots. And in the frequency domain, in the frequency methods, we use the body plot, which is much different than the root locus, but can give us information about the system. And both approaches are very important. They have their advantages and disadvantages. So we will talk about that now. Let me remind you of the body plot. The body plot is basically a laboratory generated plot. So it has some experiments. It involves some experiments. Now you take a black box. This is a black box approach. If you want to plot a body, you don't have to know what the system is like. Thereby, I mean you don't need to know the exact mathematical representation. You just need the system, and you need some measurements. What you do for the body plot is you connect the system with a p-type controller. You basically construct that feedback, and you adjust this gain. And as you would do in the time domain, there will be a critical point where you will reach. Let's say for the PID design using Ziegler-Nichols, you would just increase this up to the point where you have oscillation, and you would choose that again and that critical period, and you would come up with a PID controller. Well, in this case, we are not applying step response, and we are not looking for the critical gain. Instead of that, we have the system. We apply some sinusoidal waves. We apply a sine wave, let's say sine omega t. We start with omega, let's say 0, and then we increase our omega up to infinity or to a higher point which is sufficient for us. And then we look for the output sine. Since this is a linear system, the thing that will happen is that sine will be transformed into another sine wave. So the only difference will be in gain and phase. So we are basically observing this gain and phase change versus the frequency. So let's say we increase the frequency, but the gain drops at a certain point, and even though we are increasing the frequency, the system doesn't change in the gain that much. We might assume that this is a low-pass filter or low-pass behaving system. And here the phase is very important, since this will give us hints about the stability of the system. In the laboratory, as I've said before, you apply some sine waves, and you are observing the sine waves in the output, and then working out the difference in terms of gain and phase will give you basically two simultaneous plots that are on top of each other, which represents the body plot. Of course, I'm telling you that this is a laboratory approach, but since you have the model of the system, it's even easier. You don't have to go into the laboratory and use the system. You can also use this mathematical representation. Namely, if you plug in j omega, you will get a complex valued function that has a real part and an imaginary part. As you know, this is a Cartesian approach. If you change it to polar coordinates, you will get basically what you will be needing for the body plot, since you need a gain, which is the change in the gain of the sine waves from input to output. So you can just take the real part and imaginary part, take their squares and sum them, and then take the square root. And you change omega from a certain interval to another, so you will get a gain versus omega plot. And you can do the same for the arctangent of or inverse tangent of the imaginary part divided by the real part. That will give you the phase change versus the angle. So you can also use the system model itself. Now, it is very important that we're not, we need to calculate the stability interval for a p-type controller using the body graph. And keep in mind that the body graph will be plotted for the open loop, and we will be searching something that will give us the stability interval for the p-type controller, which means that we will have a closed loop system, and we will look for the gain that will destabilize the system, which is the upper bound of our interval. So keep in mind that we have to work out some method here, because the body plot is given for the open loop. But since the body plot is a logarithmic plot, and if you know some relations in your structure, in your feedback structure, let's say you have two transfer functions and you know that you are multiplying them. The thing that you can do is, if you know, let's say experimentally, one of the transfer functions body plot and you know the other one's model, then you can work out the multiplication body by examining both systems separately, and then let's say multiplying the gains and adding the phases. Because you're dealing with complex numbers and complex valued functions, you can easily work out body plots that you don't have available, but you can make them, you can create them, or you might just look for a certain point for that multiplication of transfer functions, but you can just find individual points and then work out the relation. So it will basically be very interesting to use the body or the frequency domain, because it has some mathematical beauty to it. Because you can, for example, you can take the inverse of the system, but the body plot will change so that the low frequency and high frequency behavior will be interchanged, because 1 divided by omega and omega have an inverse relation. So the high frequency becomes low frequency, the low frequency becomes high frequency. So that way, basically, it's an interesting method to use frequency domain approaches. Let's jump right into it. Now, we are asked to calculate the stability interval. First of all, enough talking basically, let's see the body plot, or before we see the body plot, let's try to calculate our own body plot. As a reminder, we don't have to do this for every frequency domain question or task, but it would be a good practice to start with that. Now, we are going to use the Symbolic Toolbox for a minute. Let's define our system. We have s cubed plus 11 times s squared plus 34 times s plus 24. And let me just right away define the transfer function version of this. And one. Okay. So I've told you that you can just go ahead and plug in s equals j omega. Let's do that. Let's define omega, which is a real number, and remember that you can tell the sim engine that this is a real valued variable. It will get rid of the conjugate because that's not necessary. It's equal to itself if it's real. So let's say j omega, and we will use substitute, and instead of the value s, we will have omega times 1i. So, and let's say simplify, and then maybe Pretty can help us out here. So you can see now we've plugged in j omega. Since this is cubed, you can see that this will be imaginary. Since this is squared, this will be a real part. This will be contributing to the real part. And since this is again 34s, it will contribute to the imaginary part and then real part. So we have one I here, one I here. This is basically, those two are the imaginary part, and then this is the real part. You can multiply with the complex conjugate and you will get a real imaginary part of this. So maybe we might go ahead and say, get me the real part of this and the imaginary part, and run it, and now you have the real and imaginary parts as functions. Now this might look a little bit ugly or complex, but don't worry, because you know the value of omega, you know the interval of that, because you will be examining omega starting with 0.1 or 0.01, depends on you, but and you will be stopping at somewhere 10 to the power of 3, 4, 5, 6, something high. So you know the value of omega. This will give you a real part and imaginary part, and this whole thing is a complex number. So the only thing is you have to convert from the Cartesian coordinates into the polar coordinates. Then you will have the gain and phase. Basically, since I know these, I can just go ahead and take the pretty simple and take the real part and take the imaginary part, and then calculate the square root. And look for that, and you can see now you have the square root of this here, basically, and it looks a little bit better. Now, if you plug in omega, let's say 0, you can immediately see that 1 divided by the square root of 576 will give you a certain number that will correspond to the lower bound of our gain. And if you plug in infinity, you will see that this will basically approach 0, because this will become too big, and the square root is also too big. So 1 divided by a too big value will be a value that's approaching 0. So basically, I can already tell that this will be a low-pass behaving system. Now, of course, I will basically only get the part where I have only the complex number here, that is depending on omega. And I can just go ahead and let's say look for the values here. So let's use substitute and let's give omega val. Let's say we want to try 0, 1, and 2. So basically we have a small interval where we can trace everything and see what happens. I always recommend you to use basically less points if you're starting to code something. And once you ensure that your code is working as expected, then you might go ahead and increase this interval or the grading sensitivity here. Because if you do not ensure that your code is working, debugging with too much data will be a little bit painful. So I highly recommend you to use countable, at least, elements here. So you can see that I've used substitute. I want to change the omega value with a certain interval, and I will get an array of numbers. So this is a complex array, complex valued array. You can see that this is basically omega 0, and as I'm increasing omega, I have real parts and imaginary parts, and it changes. Now here, the data I want to get is basically, I want to look for the gain, which will be the absolute value, because you can also use real and imaginary parts squared and sum and then the square root of them. But you can also directly utilize this abs function here, which will give you the absolute value, which we are basically looking for, and you can see the gain is decreasing here. And then I'm looking for phase. This will be A10, and you can use A10, you can use A10-2, which is a modification of A10. Normally, if you're using A10, you will be in the first quadrant, which means that you will have a phase angle between 0 and 90 degrees, or 0 and pi divided by 2. If you use A10-2, it will give you the 4 quadrants, 0 up to 360 degrees angle, which is handy because it will check for the sign and it will determine where which quadrants you are in. So it will give you the angle, the according angle, the corresponding angle. Now this syntax, you can just help or doc A10-2 needs the imaginary part first. So let's give it the imaginary part and then the real part, because y divided by x, so it will take y and then x. So if I do this, I can see that I have some angles, but keep in mind that these are in radiant, so I might go ahead and change them so I will have degrees. So we start with 0 degrees, we have minus 68, minus 108, etc., etc. Now the only thing that is left is I might go ahead and create a plot, and since I'm talking about body plot and my connection between those two graphics, between the gain and phase, is the frequency, so I might align them with the frequency axis, which means that maybe they should be on top of each other, not side by side, because that will be a little bit difficult to trace the exact frequency. Since they have a connection, if I have an omega value, I will have a corresponding gain and phase together. So if they are vertically aligned, I might go ahead and see what's really going on here. So we will have 2 rows, 1 column, and the first one will be the gain. Let's plot omega val against the gain. Let's have a line with so. And then I will also have a the second plot, which will be the phase. I might go ahead and name the axes. This will be frequency in hertz, and then this is basically the absolute value of j omega. I might go ahead and say that this is the argument of g omega. This will also have the frequency. This is the phase. And this is the gain. Now we can see that we have a body plot basically, but the frequency values are not enough here. I wanted to grid on, not gain. Somehow we messed that up. So now let's increase the interval. Let's say we want to have 0.1 and we want to see up to 10. Now we can see that we have a nice decreasing gain. Here we have a jump, but the problem occurs due to the fact that the A10 doesn't give us 0, 180 degrees, it gives us minus pi and pi, so it will jump basically. I am not sure, but maybe I need a modification, but I don't really remember what exactly I should have done here. Maybe adding 180 degrees and taking the modulus might help out. I don't know exactly now, but let's try out. Maybe I will take this here and put it there. Maybe adding pi will change it so that we have this here, and maybe the modulus help mod. Exactly. So maybe the modulus, let's make it let's write it like this. The modulus of phase and 2 times pi should most probably solve the issue. Or maybe without pi, I don't really remember. And then adding pi, not really. So we have kind of this, maybe subtracting 2 times pi. Kind of does the job, but not really. I am really not sure what the problem here was. Let's try to subtract first and then take the modulus. What is my value here? Or let's see what the gain is. My first value is 0.04. Let's start with this value here. Kind of helps us. Okay. But maybe I should subtract 10. It should give me basically from 0. There we go. Now we have kind of adjusted the angle. Maybe there's a function that gives us 0 to pi, I don't know, but it's really not that important now. We have this, but let's increase the interval a little bit more, and we will have a complete plot. Now, you might say that this doesn't look anything like a body plot, and you are right, but remember that these axes are basically intact, but the only problem here is that we are linearly spacing our omega values. And if I would increase this up to, let's say, 1,000,000, so 10 to the power of 6, let's say, then I'm going to have some computational issues because the sim engine isn't that fast. And even if I would have changed that, I have a for loop or some big data to calculate, and it's not a good idea. And since I'm only interested in, let's say, low frequency values, middle frequency, and high frequency regions, so I might go ahead and use a logarithmic spacing. So it will have a nice gridding in the low frequencies, and it will immediately rise to the high frequency values. So maybe using a log space, which by the way, we have also Linspace. So the difference between this here and Linspace is that you will provide starting and stopping points, and then you should maybe plug in how many data points you need to calculate. So it will give you an array that exactly starts at 0 and stops exactly at 1 and has 11 elements. So if the reason for 11 is to show you that this will be basically the same. Now if I plug this in here, you will see that this is the same vector. But if you plug in 10, then your increment will not be the same. And you can see that here. You will have a weird increment here. So keep that in mind. But we will use log space, which works basically the same, but this time it is logarithmically scaled. So if I provide -2 and 2 as starting and stopping points, this means that it will start with 10 to the power of -2 and it will stop at 10 to the power of 2. And if I provide it, let's say 11 points, at this point 11 doesn't mean anything, maybe 100 points, I will have no performance issues at all. And you can see it plotted immediately. So it still doesn't look like a body plot, and now the reason is that my X scale is still linearly increasing. You can see now at this point we have linear increment, and this is the problem. This shouldn't be linearly incremented. In order to change that, we can use a workaround in MATLAB. We can say that it should change its X scaling from linear to log. And if I repeat this to for this too and run this, will handle. Oh, this is not text. This should be GCA, and this is also GCA. Now run this, and you will see immediately we have, as expected, a body-looking plot. Now you might ask yourself if this is true or not. At this point, let's generate another one, but this time using the transfer function itself. So the control system toolbox and the symbolic toolbox. So let's compare them. There we go. Now you will maybe argue, and you can see that we have basically, let me adjust this to 3, so we have the exact scaling here. I'm sorry. And you can see it stops at 270, 268, up to 270. So it is working. It is the same, starts with 0. The only thing that's different is that we have decibels here, and here we have just raw values. So that's easy. You can go ahead and take the 20 times log 10 here. So it will give you the same plot exactly. Now, you might prefer this one or you might prefer this one. It depends on you, but we don't have to repeat the step over and over again, since we can also get this omega, gain, and phase directly from the body function. Now, the reason I've shown you this one is to convince you that it is really the real imaginary part squared and summed, and then the square root of that if you're looking for the gain, and the phase is the 8 and 2, and you should maybe adjust the function. Maybe there's a better way to do line 15 and 16, I don't know, but you will get exactly the same, and you can go ahead and calculate this. Knowing this as a fact will be very useful in design and analysis. Now, as I've told you, you don't need to use the symbolic toolbox. I can also get the data directly from directly from the body function itself. Therefore, I need to catch the outputs, magnitude, phase, or maybe let's say gain and phase to be consistent, and then omega. So this will not create the plot, it will provide you with the data that will be used for plotting. So let's run this. I have created a figure, but the body plot didn't show up. Now, if I look for the gain, you will see that there is a different structure involved. And the reason for that is you might have a multi-input, multi-output system, but since in our lessons we do not consider MIMO systems, we are restricted to a single input, single output systems, SISO systems, we can just extract the data by using this line here. You can maybe use reshape or something like that, but I like to use this one. This is the easiest way that I know. And then, oh, let's do something like this. Let's go back a little and let's paste it in here. So I have the figure itself, so I don't want to start again with this whole thing here. So I have gain and I have phase, but I will get the gain and phase from here, and then I have omega val. Let's make it omega val, and I will have the same here. Now if I run this, you can see that I have the same plot, and I have basically now the only thing I guess is that phase is directly in degrees. I'm not sure. Let's see exactly. If I multiply it, it will give me some wrong values here. It is already I have to change this, by the way. This is omega in radians, and this is not true anymore. This is 2 log and then that, and this is the phase. There we go. Now it is interesting to be able to just use the body function so that it will give us the data and we will plot ourselves. Now this has a slight advantage and a disadvantage. The advantage is that I will use this plot and I will look for some points. I will be searching for some points, and I can mark those points programmatically, so I like that way. You might prefer the body plot that is generated by the control system toolbox and use that. An advantage of that is you can right click and get some data automatically, but I like to generate my own data. Now, we didn't even start. We just had an introduction. Let's talk about the p-type controller. Now, it is important to note that if you're talking about stability and if we're in the frequency domain, then the thing that we will do is we will get the closed loop transfer function and just plug in S equals j omega. But the important part here is to use basically the open loop body plot. Since I didn't design any controller, I don't have exactly the transfer function that is usable for a body plot. I'm not able to generate the body plot. I need the value of the p-type controller. So let's look for a unit feedback for starters. Let's assume that k is equal to 1. If that's the case, then my transfer function will be k times g divided by one plus this, and since k is equal to 1, it will be equal to just this expression, g divided by 1 plus g. Now, and think of this remember that we will be plugging in S equals j omega, and this is a complex valued function. Now, stability, or maybe for the frequency domain, instability is important. And if you remember the definition, it was something like if we have a stable system or marginally stable system, this system will start at any point, any starting initial value, and it will settle down to a certain equilibrium point. Since we are a linear system, it will be zero. So it will basically use its energy and it will decay to the origin, or zero. And if it's marginally stable, it will be in a bounded area. But if it's unstable, it will not decay, it will not be in a bounded region. It will increase and it will approach basically infinity. Now, this approaching infinity is here really important. If you have a fraction, and if this is a fraction takes some values, in which case, for which value, or for which case can we get infinity? Now, basically the response here is that 1 divided by 0 will tend to infinity. So we will check for stability by checking the denominator of this closed loop and if it's equal to 0 or not. If we have a certain frequency, and for that frequency our closed loop transfer function becomes the expression 1 divided by 0, so if we get a 0 division error, then we will have instability. Now, how is this possible? Basically, 1 plus g, for this case, 1 plus g, should be equal to 0. And keep in mind that this is j omega. We have these S's here. Now, 1 plus j omega should be equal to 0, which implies that I should have this equal to minus 1. So keep in mind that this is not the absolute value, this is not the angle, this is the transfer function, the fraction itself. So if I look for the body plot, and if I will be utilizing the body plot, then I might go ahead and change this Cartesian value minus 1 into polar coordinates, which will be 1 and 180 degrees. So basically, the system should satisfy two conditions based on this, line 33. The absolute value, or the gain, should be 1, and at that exact frequency, because we have a fixed frequency here, omega star, at omega star, if the gain is equal to 1 and the angle is equal to minus 180 degrees, then we have a division by 0, which will give us infinity. And basically, even if I apply a bounded signal to the system, even if I have a constant, something like that, the output will tend to infinity, which is basically our definition of instability, which means that up to this point we will have a stable system, because I'm increasing omega and the stuff changes, but I am crossing 1 and minus 180 degrees. So, but keep in mind that k is not equal to 1. So let's introduce k back. We will have something like this. But the fact that we are looking for the denominator, and that should be equal to 0 for instability, or that at the point of instability, is remaining unchanged. So I can plug in everything here, and I should look for k times gj omega equals 1 and minus 180 degrees. Now, at this point, the thing that I've talked about earlier was that you can use the body plot, and if you know the expression of a certain other transfer function, and if you have a multiplication, it's very easy to deal with this, because you can work out using this relation and you can find everything you want. Now, remember that if we are using k, which is an unknown, this unknown k is a real value, because we are in the real domain. The only thing that will be complex is the fraction itself, or s. Since we are plugging in s, that's the reason why the fraction of the transfer function depending on omega is a complex value. So k in itself is the controller, and the gain controller should be a real value. It cannot be an imaginary value. So this means basically that the angle of k will always be 0 or 180 degrees. It doesn't matter. That's only a sign change here. So I can safely assume that the angle contribution here will be 0. If it's negative value, I will come to that later. But since k, in the sense of root locus for the p-type controller, I'm maximizing k in the 0 infinity interval. And then I reconsider the whole system in 0 and minus infinity. So we don't use them simultaneously. So if k is a positive controller, which is preferred, by the way, no one wants a negative valued controller, even if it's a static controller. No one wants a static controller. That's even a different story. But, well, I know basically that k will be contributing to the angle with 0 degrees, which basically means that it will not contribute to the angle. So this is very important, because if I take the argument of k times this here, this is equal to the argument of k plus the argument of the system, the open loop plant. Since I know this will be 0, I can neglect that. So the only thing that is left is this here. Now I can attack this problem by first searching the angle condition, and if I'm crossing minus 180 degree, that frequency is a candidate for instability, because it also needs to satisfy the other condition. So I'm using this data here, and I'm find omega star. If I have this omega star, it's also easy to use the absolute value of this and equate it to 1. Now, the absolute value can be written as this here. It is the multiplication of absolute values. And since I know omega star, I might say that this is a value, and it is. So I can convert it into this expression. And I can see now, I can get, and since k is positive, by the way, the absolute value can be dropped here. So the k value is 1 divided by absolute gj omega. So the step 2 here is basically calculate this. Now, what did I use? Well, I used the fact that the closed loop is a fraction, and I considered stability so that this fraction should tend to infinity for some value of omega and k. And I've just basically worked out the facts, and that's it. I've used what I have available to me. Now, I can use the body plot for this search here. And I can see now that somewhere around here, we have minus 180 degrees. Let's try this one. I'm approaching it basically here. 184. It's not easy to click that point. Let's assume this is almost 6. So omega is almost 6, so I have to go ahead and click here and look for that value. Now, for the sake of simplicity, I will drop this logarithm here in order to see what the exact value in that area is. Now, I can see now that somewhere around here was 180 degrees. A little bit more to the left. A little bit more to the right. Since this is a logarithmic scale, it might be not possible to see exactly the point. Maybe we should increase the gridding here. That would be a good idea. But since this is only the part where gridding is automatically acquired, you might give your own omega, so you can just say log space and then maybe -1, since that's only the necessary part. And I guess 1 is also sufficient. And let's say we have 500 points. Let's see now. So I'm focusing basically on the area of crossing now, somewhere around here. A little bit to the right. No, let's drag it to the left. A little more. Okay, maybe let's have the lower bound to this. So this is 5.803. So hopefully 5.8. A little bit to the right. Just a little bit more. Tad more. There we go. I've catched that point. So the inverse of the y value will give me basically k. You can see the argument -180. This is the argument. I'm looking for -180 degrees. This is this point. And then I have a frequency, and then I'm switching the graphic, and I'm again looking for this value. So this is why we use them vertically, since I can easily look for the same frequency using the other graph. And then I get that it is 0.0028. 0.0028838. So the inverse of this will give me the upper bound for k. And it is 346.21. So if I use this for feedback, let's have figure 2. The step response of the feedback using this value times gs, 1 should give me an oscillatory step response. And you can see that here. Now I've chosen that point and I have looked for that point. This is tending to the marginal stability, because at some point we will have an exact oscillation and then it will tend to infinity. So this will be basically the upper bound. So I can use 0 up to 346.21 even to get an interval. Now it's a little bit painful for me since it's a logarithmic scale and I have to click it, and if I change a little value here I have to repeat this process. So I don't like this approach. Maybe we can just go ahead and define something here, an error vector, and that should be of the same side of omega. Since I have, for every frequency I will have an error, and this error will be, let's say, error. And what I'm trying to do is I will use the first step here in order to get the omega. So you might say, why aren't we searching exactly for -180 degree? And my response will be that you might not have that value, but you might have a value that's close to -180 degrees, as in the case of where you can see in the graphic that we have -179 point something. So I want to approach the vicinity and I want to just use an approximate value. That's enough for me. So that's the reason why I should do something like this. Every point that exists in this graph should give me an error, and this error should be equal to the difference between -180 degrees and my phase angle here. Error phase angle. So let me show you what it looks like. What the error itself looks like. Oh, I didn't say size. So there we go. Now let me see. Oh, this is already a negative value, by the way. So this shouldn't be like this. I should add 180 to this because I have minus 180 degrees. And you can see, since I've used the absolute value, that it kind of corresponds to the frequency where I was working. And the minimum value of this absolute value will give me the best approximation. So let's take the minimum value of this. I don't, maybe for demonstration, I will show you the value, but most of the time I only need the index. So which element satisfies this condition? That's enough. I don't really need the value, but I will show you the value and the index simultaneously. Now you can see that index 442 gives me 0.26. So my error here is 0.26. Or I can also show you the phase angle that is at that index. If I run this, I have minus 180 degrees, 0.2682. So this point gives me basically the upper bound. Maybe we can just go ahead and change the index to -1 in order to be able to get this from the left. So I'm choosing the one on the left to get this 179.6691. So I'm basically trying to be conservative. If I have 180 and calculate something like that, then maybe I will catch a point that is already past the critical upper bound. So this will give me the upper bound. So let's get rid of the value. I don't care for the value, so just put in tilde. And the index I will be using will be index equals index -1. So this is not that much necessary, but I want to be safe, so I'm doing this. So remember that the next step was to get the absolute value here. So since I have the index, I can get the gain index because both the gain and phase data is aligned, so it's exactly the same point. And you can see that this is 0.0029, which corresponds to this area. So basically it's repeating itself. So, and my K crit here, critical value upper bound, is the inverse. That's it. So the graphic itself tells me now that this is the upper critical bound, or the upper bound for the critical value. So I have basically the upper bound for the stability. Now, remember that this was the positive analysis. If you know root locus, you know that the positive root locus gives you the upper bound for that. And if you have a negative root locus, you can also get a bound from there, and it will be between those two values. Now, in order to be able to search that point, we have to assume that K is basically negative. So I'm not looking for 180 degrees anymore. I have to look for 0 degrees because the K value will contribute minus 180 degrees because it's negative. So the system itself should have 0. In this graph, I can see that I'm approaching 0, but I'm not reaching 0. Maybe I should include the lower part a little bit more. Maybe let's make it -6. And I have a certain value here. So basically at this point, I can assume that this is 0, and a better approximation would be somewhere around here maybe. And at that point I can look for the gain and take the inverse. So I have this gain here, 0.041 something. So I can take the inverse. So here the approach might be maybe -5 here, doesn't matter. to get the first gain and calculate the inverse of that. So the first element, it starts from 1. So 24 is the value, but keep in mind that I should put in a minus sign because this is the minus root locus. So I can now assume, and maybe I should use a little bit more here, I can assume now that my system is stable in the interval of minus 24 and 300 and approximately 340. And why did I look for 0? Because I know if k will be negative, then the contribution will be 180 degrees, minus 180 degrees. So I might go ahead and look for 0 contribution of the system. Or you can also look for 360, since this is periodic. But if my plot is between 0 and minus 200, then it makes sense that I'm looking for 0 and minus 180 degrees. So basically we're looking for k times 180 degrees, k can or m times 180 degrees. Here m can be negative or positive, but I'm looking at those points because those points are critical for me. So if the angle contribution is 0, then I have the negative root locus effect kind of. I'm looking for that stability bound. And if I have the contribution of minus 180 degrees of the system, then I'm looking for the positive root locus. Most of the time the negative bound is not that necessary, but if you're if the task is to find the interval using body, then you might include the negative interval also, because unless you're including that, your answer will be incomplete because it's not the most general interval. It is a sub interval basically. So I can see it is between 24 and 339. So let's look for this information using the time domain. So in this root locus, I have to click somewhere around here because this is the j omega axis crossing here. Hopefully. And you can see that the 344, since I've used -1 and a bit more conservative in order to end up with a stable bound, you can go ahead and calculate this 344 if you're not that conservative. Let's basically try this point here. It is 350, and you get what I mean. Because body plot is not that much detailed, you might miss the exact point and you might end up somewhere here. So being a little bit conservative makes sense in that case. Or you have to increase your grid, but still it is important to be conservative. And let's look for the negative root locus and see what happens here. You can see that here is this crossing, and hopefully I can see that this is 20, and I am still again so I can see I'm basically I did find the same thing in root locus. I couldn't catch that point, but it is approximately -24. Is there a way to calculate this using the transfer function itself? Of course, you can plug in omega and you can look for the solutions where you have the angle condition satisfied, and using those solutions and eliminating the unnecessary ones or the ones that we're not interested in should give you the omega value, and you should then get the gain value and take the inverse and acquire this interval. So basically, if you're using body plot, I like to do this. I like to define an error signal, and then I like to look for 180 plus phase I, because phase I is minus 180 degrees. So this is equal to phase I equals minus 180 degrees, but I'm looking for the error. I'm trying to be conservative, and I get the point automatically, and then I can just get the gain and the frequency. So now this is basically A. And it took a long time But we did an introduction and we looked for that. Now, B is very, very simple if you know the relation between overshoot and frequency domain. And in the time domain, if you remember, we were looking for a zeta value. So the thing that we did there was we took this overshoot. We had a formula minus log overshoot divided by the square root of pi squared plus log overshoot squared. And this would give us a zeta value. And then in the root locus domain, we were just plotting we were just looking for this zeta graph, which is basically a line. So the crossing or the intersection of the root locus and our zeta line would give us the solution, and that was it. And since we can see that in the root locus plot, in the positive root locus plot, let's have the positive one here. Since I found this point of stability, and since if I have any zeta value, I can see that this zeta value should be before I hit this point. So by that I mean it should be earlier in the case of the body plot itself. So if somewhere around minus 180 degrees I have instability, I should, since you can see from the gain, I'm basically increasing the frequency. So for this plot, I can see that maybe I'm looking for somewhere here. So I need a certain phase angle that corresponds to my behavior, and this phase angle is less than minus 180 degrees, or it's somewhere around here. It can be here, it doesn't matter, but it is somewhere on the left of the critical point. So basically I'm trying to find somewhere a point somewhere here. So there's a relation, and even I couldn't memorize this relation because it is very ugly looking. So I will show you that. Before I do that, before I transition into B, I want to show you that the advantage here is to be able to plot the point of interest. You can just go ahead and use this index value. You can look for the gain here of the index value, and you can put, let's say, a circle around there. Let's say line width of 2. This should go here, which means that I should calculate everything before I plot everything. So let's take this and put it in here. So I can plot this here, and I can also plot the face here. So let's say these should be black, and if I run this, now I can see that I've chosen this point here, which is minus 180 degrees. So maybe increasing the interval will give a better plot here, and maybe minus 3 is sufficient here. So you can see that basically I'm choosing this point, because this point is the point where the angle is minus 180 degrees, and my gain value is a certain value, and I take the inverse, and I get 344 approximately. So what I mean here is that if instability occurs here, those are unstable too. I'm looking for a more stable point with a certain zeta value. And this should be basically here, because I'm again interested in the angle, and this angle should give me basically the gain, and I will again take the inverse of the gain, because I'm again considering the p-type controller. So the p-type controller design has a very standard algorithm. You're just looking for, if you're looking for a stability point, you're looking for minus 180 degrees, and if you're have some overshoot, it will be something else, and you will be again utilizing the phase plot. And if you have a certain frequency, you will go ahead and use the gain plot and take the inverse of that gain, and that will be your p-type controller value. So let me show you this plot can help you in looking for that point. We've generated the same here. And I have a more formal representation here. We are plugging j omega, and the argument of this whole thing should be equal to that, and this is satisfied at 5.8. You can see that this is the value, and you get here. And as I've told you, I didn't update my notes, but you can see that this is not the conservative one, so being conservative is a little bit better. Looking at the pools, you can see that this is unstable, the unstable point, and you can use the same code here. Now, I've told you that using the zeta value for 10% overshoot, we are familiar with this, we know this, and we use zeta. Now, there is a correspondence between the phase margin and zeta, and phase margin means how basically is a measurement of how much I should go back from the point of minus 180 degrees. Let's say 10 degrees, I should just add this 10 degrees. This is my safety distance from the minus 180 degrees. So phase margin is basically that. And the definition is the amount of phase addable to the phase of the system so that instability occurs. So this is basically how safe I am. If I have 70 degrees, it's more safe because it is at minus 110. So there is 70 degrees of distance to the instability point. But since we know that if we get further away from the instability point, our zeta will be increased. So there's a relation between that. And this relation is exactly the inverse tangent of 2 zeta divided by the square root of minus 2 zeta squared plus, I'm not sure if this is a square root or was it a nth order root or fourth order root. I'm not sure, but I guess this was the right representation. 1 plus 4 zeta 4 to the power of 4. So this is even uglier than this. If you thought that this was not memorizable, think about this one. So now using the zeta value, you will just get an angle, and this angle should be added to 180 degrees. So I should be 58.6 degrees distance or away from minus 180 degrees. So basically I should be on the left. So let's go ahead and use this data and search for that point. And k crit, let's say 1 and k crit 2. Or let's say positive or negative. The stability interval is, and then something like this, information is, and then we will have num to str k crit negative, something like this, and then num to str k positive. And let's get rid of this root locus here. What did we mess up here? There we go. We can see that the interval is this. Now, basically what I'm going to do is now I will search for a point where I have plus phase margin. So you can go ahead and type the phase margin formula, but what I'm going to do is, because I'm a little bit lazy, I will go ahead and use the value directly from my solution manual here. So again, we have an error, but this time around it should be index 2. And let's do the same here. And the thing I'm going to do is I will subtract my phase margin and even a little bit more, I guess, 10, let's say 10 degrees. I want to be a little bit more safe because it might be the case that I am using the incorrect point of instability, so I want to be safe, just to be safe. I don't need this anymore, and let's say this is K here. This phase margin needs to be defined. Usually, or just let's do the right thing and use this overshoot divided by the square root of pi square plus log of overshoot squared. And then we will use the A10 of what was it again? A10 of 2 zeta divided by the square root again, exactly. Square root of minus 2 times zeta squared plus the square root of 1 plus zeta to the power of 4. 4 zeta to the power of 4. This should give me that. Let's see. And most probably I didn't define overshoot. It was 10%. Times. And this is in radians, so I have to convert it into degrees. Now you can see that this value is basically the same value from the PDF. Now I can add this to my searching point and it will help me. So let's display this phase margin. Overshoot num to str overshoot and then corresponding phase margin is num to str phase margin. Now if I run this, I can see now, oh, so that's better. Now the stability interval is this. The 10% overshoot corresponds to phase margin 58.6 approximately, and I can also display the gain that I have. So maybe the p-type controller is k and that's basically it. Now I can see that it is 66. It's far away from the instability point here, and I can see that. Now I might go ahead and look for, since I have this here, I can just look for the step info of feedback of this k times gs comma 1. So run the section, and we can see now I have a certain overshoot. Now it's arguable that the frequency domain method will work as expected, because now the frequency plot on itself is a little bit problematic, since we are using the logarithmic scale. So any little error will be amplified here because you're in the logarithmic scale, not linear scale. That's the starting point. And then we also have a problem where the relation doesn't work that good. So that's another thing. Maybe let's, for example, change it so that we have a lesser overshoot, and you can see that it's not decreasing as expected. But let's say we want to have 20% overshoot, so this is very bad. It is 26%. Maybe it works a little bit better in the area where it is close to the stability point. So kind of problematic. You can see now I have 30 degrees, and this is 31 overshoot value. So basically what I'm trying to tell is it doesn't work that good in the design area, but then the question is, why would you use the frequency domain for time domain criteria design? So basically, if you want to design settling time, overshoot, these kind of properties, then the time domain approach makes more sense, because you're starting with a settling time and overshoot. Here you're kind of manipulating the frequency domain data that you have so that you get a design. Now, of course, it makes sense to use frequency design, but not for linear systems where you have the model available. Consider this: if you have a body plot and you have used the black box approach, then this is actually the best thing that you would hope for, because this relation helps you to design settling time, not settling time, basically. It helps you to try to design for an overshoot value as a specification, but you are not aware of the model. You don't know what the model is. Somebody gave you a body plot, and that's it. Basically, you need only the body plot itself to come up with a p-type controller, and that is really powerful. If you think about the time domain, you need to know the exact representation, at least approximately where the poles and zeros are of the plant, and that's corresponding to the mathematical model. You need to know the model in order to come up with a design. But this trade-off is kind of makes kind of sense. If you know the system model in detail, then you can come up with a detailed design method that will give you a more sensitive design, a better design, and you can use that method. But if you are lacking the mathematical model information, if you don't know exactly the model, if you have a black box, then your method will most probably give you a rough idea about the controller, not the exact controller. So if you have systems that can give you body plots, you can just go ahead and design for those systems using this design method. But if you have the model available, why are you bothering with the body plot or body method, frequency method, if you can just go ahead and use the time domain approaches? So the algorithm is as follows. If you have the model, go ahead and use this model and the time domain approach. If you don't have the model, if you have an idea about the model or a body plot, then maybe the frequency, opting to the frequency methods will be a better idea. So they're complementing each other, basically. So in the laboratory sessions or in homeworks, that's not the case. You will use both the frequency and time domain approaches because we're at the stage where we're trying to learn these methods. But in the real world, if you're trying to apply them, then this rule of thumb is very important. If you have a model, if you have a detailed model, go ahead and use time domain approaches. If you have an idea, a body plot, a frequency plot, some data that is not exactly describing you a transfer function, then you can just go ahead and opt to the option of body, because you don't have a transfer function. How will you come up with a dominant pole pair and try to design for settling time overshoot and all those specifications? So basically, this is trying to show you. And as I've told you, the point where this is working very well is the point where the phase margin is very low, so you are in the danger zone, so this helps you. And that's also the reason why I have added 10 degrees, because it works better in the danger zone. So being a little bit more even conservative is even a better idea. If I'm somewhere around here, or if this formula would have been working better for zeta equals 1 or the vicinity of that value, then I wouldn't have to need to add this 10%, 10 degrees safety margin. It depends, by the way. You can use 5, you can use 12. Those are the common intervals. If you are not feeling that safe, increase the amount. If you're feeling more safe and want to have a better design, you would most probably try to use 5. Okay, so let's again return here. Now we have used basically these here. We've answered these here. So we might go ahead and add a phase lag controller to the design that will change the steady state error tenfold, and using the body graph. So I will come to this, but let's transition into this one, because it's again about stability interval, and since I've made you a point, I will now demonstrate to you that point. So it's a good time to jump to D and then back to C. Now let's come to the editor. Let's basically let's copy everything and then delete it. That's maybe better. So I'm going to define the system, and I will use this as a template from now on, and you might go ahead and do the same, because most of the time you will repeat this for p-type controllers. So, and remember that I can add this delay using the IO delay and the 2, so I have 2 seconds of delay. And I'm trying to find the stability interval, so that's it. So I will get this body plot, I will get the magnitude and gain, and I want to look for minus 180 degrees, and then I will look for the best and conservative approximation of minus 180 degrees, and I will get the stability interval. And basically this stuff is not needed, and I can plot these points here, and that's it. I will not change anything, because it will give me automatically the point where I need to calculate or where I need to carry out my calculations. And that's it basically. I did not bother if this is a delayed system or if it is just a linear system with simple poles. Now, this is what I mean by you don't have to know the exact model, or you can use the black box approach here. The only thing that is necessary is that you need to have a body plot that is available to you. And that's it, because this applies, well, of course you need a linear system, by the way. For the nonlinear parts, I cannot help you with that. We have to learn nonlinear control for that area. But in the linear domain, I can tell you safely that if you have any linear system, even if it includes delay or not, you can use the body plot. It will give you a an idea basically about the stability. Now we can see that -2 and 2.15 gives me the interval, and keep in mind that root locus is not available here. So I cannot find this interval using directly root locus, if you remember. Because we have infinite amount of poles and zeros, because of the e to the power of -2 tau, 2 s. So what I can do is I can just use the Body Approximation, and this will give me an idea about the stability point, which is also the case for the body plot. Of course, I should use this, and I should plot this in figure 2. Let's run this. So you will get this, and if I click somewhere here, I will get 255, which was also the value calculated here. So I might use a better approximation, since this wasn't representing the exact point here. And 2.16, so it approaches 215, maybe the 20th. Okay, that's maybe too much because there will be too much points, but maybe the 10th order. Something is happening around here, as you can see. I'm not even able to see which one of these will give me the exact value. I have to try everything out, and then I might assume the lowest value of these are is the stability overbound. But I can easily check the body plot and get this value here. So, and another fact about the delay or the delayed systems is that I can see that the angle gets out of control, interestingly. And this makes sense because I'm looking at the argument of e to the power of tau s, or if I plug in sj omega, this is tau times omega will be the arctangent of tau omega, j tau omega would be the result. And tau omega is basically subtracted from the original phase, and since omega tends to infinity, this will tend to infinity, so the angle here gets out of control. And you can see now, adding delay to the system affects your stability dramatically, because it will subtract an amount that is depending on the omega value here and the delay, the amount of delay, so tau times omega. So it is really important to note that if you have a high delay, then in high frequencies you might have been lost, because it tends to minus infinity. So since we are only interested in 180 degrees, the higher the delay, the lower the upper bound for stability using a p-type controller. So I can immediately see this fact here, and it is really important to note this, because in root locus we were not able to say this theoretically. Maybe numerically, by trying by trial and error, you can see that okay, if I have more delay, I will have a worse performance, or my interval will narrow down. But being able to state this using theoretical proof is very powerful here. So the body plot, and the reason why we still know and hear about this body is the power that lies behind it. It is very powerful. And basically, this tau omega is very important, as I've told you. There might be interesting questions. You might ask someone, what is the maximum addable delay to a system? What you have to consider is that tau times omega will be the phase margin, because the phase margin is the safety distance from the instability, and you are asking to find the point of instability. So maybe you should use this phase margin and tau omega. You should equate them, and keep in mind that one of them is most of the time degrees and the other one is in radians. So you have to keep in mind that you have to do some conversions, and then you can just find how much delay I can add to a system. Also, this gain margin definition is the same. How much gain can I apply to the system as a p-type controller so that I have instability? Well, basically that's the upper bound k critical that I'm calculating here. So gain margin and phase margin are based on this body plot, and if you know the mentality or the philosophy behind the body plot, then you will be most probably answering them correctly, because the margins, the word margin is here very important. The distance to the safety, in safety, I mean, to the danger, the safety distance to the danger point. And this danger point can be minus 180 degrees. So it is basically a minus 180 degrees. So if you're looking for an angle, then the distance to minus 180 degrees is your phase margin. If you're looking for gain margin, then that's the p-type controller upper bound, basically, because that much gain can be applied as a p-type controller to the system so that we have the point of instability. Now, there's also this phase lag controller design. I will quickly show you using my solution manual, and the reason behind that will be obvious in a second, because it has a very standard algorithm. You have to do carry out the steps step by step, and that's it basically. So there's not that much flexibility here, as there's no the flexibility here. You are basically looking for the angle where the angle is equal. You're looking at the frequency where the angle is minus 180 degrees. You take that frequency, plug it into the system, look for the gain, and take the inverse, and that's it. You cannot basically try to manipulate this method. This method is fixed. And the same here, because you have to use this overshoot value, convert it into the zeta value, and then convert it into the phase margin. Add this phase margin to the minus 180 degree danger point or instability point, and then you will end up with a new angle, and then you search the system for this angle, and once you get the frequency where this is satisfied, you will use the gain and take the inverse. So basically the method will be shown in a second. You apply method A to D, and the only thing that changes is basically e to the power of minus 2s term, and that doesn't affect you if you have the ability to use MATLAB. In the older days, where we didn't have this pandemic and we were having some classical exams, we did ask questions like, we calculate the stability interval for this system, but we were providing you only this transfer function part here. Without the delay, you were asked to try to take this delay into account manually. So it is an interesting approach. Maybe it could be the case that these questions may come to you. You can verify your answer by using MATLAB, but it is really important to know how to use the body of this part and to manipulate that body data so that you're searching the right point. So it is an interesting problem. So as I've shown you these parts here, you can see that I have calculated a certain controller here by taking the inverse, and if you use this value here, it will give you basically the angle condition. Instead of minus 180 degrees, you can see I should have used minus 121 or adding some safety minus 110. It depends on you. So how can I design a controller? Well, first of all, since the steady state error is obtained as 0.22 and my controller should decrease it tenfold, I'm trying to find the gain where I will have 0.02. So this is the reason why I have divided this into 10, because tenfold. So I'm looking for the steady state steady state error here, and this is the expression of steady state error in terms of steady state values. So my control is k, my steady state gain is 1 divided by 24. My closed loop gain or my closed loop steady state value will be equal to this. So this is error. This will be the steady state value. I'm looking for the steady state value. So I have to calculate the value of k. And I know that I should apply this, but since I'm first designing a p-type controller and then the phase lag controller, this means that I should improve, but I shouldn't change the transients that much. So my gain is 1024. And then I use the body plot given in figure 4, which is this one, which isn't the same body plot as of the system, because I have to embed this into the system. So my new body plot will be generated by the transfer function times k. So k times gs. This is the body plot of k times gs, not gs itself, because I am embedding the p-type controller to the system. So I have adjusted the gain, and this gain will basically affect the body plot. So the new body plot will be used for the same point, but I'm adding 10 degrees because I have a phase lag controller, and the difference between the pole and zero angles should be around less than 10%, so 10 degrees. So adding 10 degrees will account for the angle contribution of fs. Why do I need to add 10 degrees? Because I am going to design a controller that will be in the bound of 10 degrees, that will be contributing 10 degrees at most. So since this is a phase lag controller, this doesn't introduce that much of an angle contribution, because it shouldn't change the transients. If you change the angle, the transients will change. Because you can think about this of the overshoot value. I told you that 10% overshoot corresponds to 58 degrees of phase margin. If you're contributing angle to the system by designing a controller, then this phase margin will change, and since phase margin directly relates to zeta and then of overshoot, if you have an angle contribution, this means that you will basically change the overshoot, and the transients are affected by that. So what we are trying to do here is we are trying to not to change the angle, but to change the gain. So of course that's not possible if you have a phase lag controller, but it will have minimal effect on the phase property of the system. So I'm just accounting for that. If I have 10 degrees of contribution at most, then I should add this and be a little bit more safe and design and look for the angle or the frequency where the angle condition or the angle of the feed forward path basically is minus 111. So this angle should be valid for k times this times gs, because my actual controller is k times this here. But this is the phase lag part, and this is the p-type p controller part. So they together build this phase lag controller, because the phase lag controller with gain 1 is introduced here. So basically I'm adjusting the gain, and then I'm trying to add a phase lag part where I do not mess up the angle condition, and basically that's it. Of course you can go ahead and use only a p-type controller, but if you are trying to use a phase lag controller, that will work obviously better than the p-type controller. We can add 10 degrees to the stability, and the point where k times gs satisfies this angle is 2.1 radians, and using this I will get some values about that. I will divide 10 by that frequency value, which will give me tau, which is a parameter of the controller, and I'm not sure why this is so, but the algorithm tells me to do this, so I'm just following the algorithm step by step. Basically it says that 10 divided by omega gives you tau. This relates I I can understand why, basically, because I'm looking for omega times tau at most 10, so it gives me the highest possible value of tau. So I'm placing, using this, the zero of the system, and then I will look for the gain at that frequency, and that will be alpha. So basically my resulting controller will be this times tau s plus 1 and alpha tau s plus 1, which corresponds to this here. So this controller, as you can see, this is a phase lag controller, so it's in the vicinity of the origin, and you can see basically the effect, and you can see that 10 times the steady state error will be decreased 10 times. You can see the effect here. The overshoot property didn't change, but it's arguable that the settling time did change, but you can see that the rise time didn't change, the delay time didn't change. So the only thing and the drawback of this controller design is that the settling time will change, and since you have a pole zero pair in the vicinity of the origin, you will have this interesting effect here. So that's unavoidable. If you go ahead and use a PI controller, you might get a better control scheme here. But if you're asked to design a phase lag controller, this is how you do it. And basically, you're looking for a higher gain value, so you design a p-type controller that satisfies your gain or steady state error or steady state gain values. And once you've adjusted your gain accordingly, you will look for the same angle or phase margin approximately, but you will add 10 degrees of safety, and then you will use 10 divided by omega, where omega is the point where you satisfy the angle condition, as tau. So you will place a 0 using that value, and then the gain at that point will give you the alpha value, and that's it basically. And once you write this code where you are searching for this angle, which we have written by the way, you will just change this or update the code where this omega will be used to calculate 10 divided by omega will give you tau, and then at that gain you will just get the alpha value, and you're basically done. So I have shown you the code that will most probably be used for most of the body based designs or frequency domain designs. So that's basically it. Now I can see the effect of the phase lag controller. It has an angle contribution in this area, and it did change the gain a little bit, so it's not the perfect design here. The stability interval of this, you can see that even 1 point something reaches the point where 180 degrees. So this is way faster than a system without delay or the same system without delay, because tau times omega, as omega increases, this will become faster and faster and will get out of control. So you can see that this is basically the interval, and you can see the response here. You can see also using the minimum phase part and the delayed system. So this is basically 10 divided by s squared plus, what was the system again? 12 divided by s squared plus 10s plus 24 is basically this red part here, so without the delay. And if you add the delay, you can see the effect here. You can see also that the gain didn't change because the absolute value of e to the power of minus 2s is equal to 1. So gain remains the same. The only thing and the only contribution here is the angle, and it makes kind of sense because e to the power of minus tau s, if you plug in s equals j omega, it immediately becomes the phase angle. So there's not even a inverse tangent necessary. You have just tau omega as the angle contribution of the delay term. So that's basically it for the frequency domain of today's lesson. Well, there are many methods, and we could cover more and more. And basically, there's also a phase lead design method, and there are some little variations of these questions, but this is the base basically. If you know basic body and some of these control methods, you will immediately adapt to a new algorithm or method that is based on frequency methods. So see you in the next lecture. Hope that this was helpful for you.